if so, we can measure the propagation velocity. But this propagation velocity of the sound is directly connected or is connected to the Young model, the coefficient K. So that is why we are able to identify this coefficient. We are able to identify this coefficient. On the other case, this coefficient doesn't depend strongly on the strength of the bone. So this one, rho density, depends more stronger, several times stronger. So that is why we can assume that this coefficient is more or less a constant. However, this one is a varied one. So if we have the shift of the or changes of the velocity, this means that we have the change of the bone density. So that is why this is an indirect measurement through the velocity to the density of the bone. And so by this way, you can identify what is the density of the bone. Is the idea clear? Please, questions? Vai visi ir skaidrs, lūdzu, jautājumi? Vai ir skaidrs, lūdzu, atbildiet?
Jā, ir skaidrs.
So the second technology that is a very popular in medicine and diagnostics, sonography. So there are two ideas. The first one is based on the propagation of the ultrasound wave through the patient or through the organ. So if you don't have any resistance for the sound to propagate, so the detector is able to detect the signal. If there is a resistance, for instance, some organ, maybe some stone within the organ, or for instance, in kidney or something else, so the sound doesn't propagate, and the detector doesn't see this sound signal, this beam. So there is some shadow. So the other one technique that is most popular, reflection. So the sound reflects from the boundary in between the organ and the environment, and the reflected sound is detected. So if we have the reflection, we have the signal here. If you don't have the reflection here, we don't have the signal. So that is the idea for sonography technique, and we are able to see the organs by this way, and we are able to see the motions of the organ, and so we'll speak a little bit later about this. So the questions here, jautājumi lūdzu, vai ir skaidrs?
Ir skaidrs.
Yes. Oh, sorry. So this is a short movie about two techniques. The first technique is the sonography that gives 3D image, and the second one is a holography technique that we don't speak about the holography today. The holography technique gives actually projects the ultrasound image acquired in 3D space that people optically project in 3D space that people are able to see. And now you see the organs that the images of the organs that became acquired using the ultrasound, and after that transferred through the holography technique in 3D space. So have a look. So perhaps no sound here. Sorry.
This is a fully grown, live and beating child's heart. These hyper-accurate holograms were produced during clinical trials conducted at Schneider Children's Medical Center in Petach Tikva and presented three-dimensional medical holograms, no longer science fiction.
Okay, to my mind, very impressive. So the second technique that we use to identify motions with sonography technique is based on the Doppler effect. And now I tell you, I believe that you know, but just to repeat, what does it mean, the Doppler effect? So this is the sound generation center. The sound waves are excited here. This is the first wave. The sound generation center doesn't have any motions. It's stable and generates the second wave. So this is the second wave. Now the first and the second became extended or propagating. First, second. And now the sound center generates the third one. So everything is symmetrical. You see the concentrated circles. And now we change a little bit the experiment. So definitely the distances between these waves in any direction is the same, lambda. Now we change the experiment. So this is the sound generation center, the first wave. The sound center is moved. So the first wave still propagates by the same way as before, and the second wave is generated from the new place. Now we generate the third one. Again, the sound center is moved. The first, the second, and this is the third. And have a look now. The distances between the waves are not equal. For instance, from left to right, the distances are shorter between the wave than from right to left. So if the distances are shorter, this means that the frequency of the wave, you see the frequency of the wave, the frequency to meet the wave here is higher than in this direction. So because of the sound generation center, the frequencies of the sound are changed or are different in different directions. Is this clear? Please reply. Uzatbildiet vai ir skaidrs?
Yeah.
So this is a Doppler effect, and definitely it's very easy to predict that this density, actually the frequency of the sound in this direction, depends on the motion velocity of the sound generation center. The same here. So this is the idea to measure the velocity of the sound generation center. So this is the formula that demonstrates that really the frequency depends on the wavelength. The wavelength is shorter here, so that is why the frequency is higher. So now we have the sound generation center, our sonography machine, and this is the organ. And the organ has movement. So the organ has a movement with a velocity c. We direct the sound beam to this organ. The beam has a frequency nu, and the beam is reflected. However, have a look. Now this organ by this center is considered as the sound generation center for this red reflected beam. And definitely because of the motions in this direction, the frequency here of the red one differs from the frequency that we sent before. So now if we go to measure the differences between these two frequencies, we can identify the velocity of the center motions, of the organ motions. So the formula is very simple. So the difference in between the frequencies is directly proportional to c, to the organ motion velocity. And from this formula, if you know the velocity of the sound, definitely, and we know definitely we need to measure this difference. We can identify what is the velocity of the organ motion. What are the organs? Heart, blood. Blood has the particles, and the sound beam reflects from these particles. The particles have motion. We can measure the average velocity of blood. We can measure pulses of the blood. And so this is a very popular technique today. Some questions, please. Vai viss ir skaidrs, lūdzu jautājumu, lūdzu atbildēt.
Tas vai ir skaņas izplatīšanas ātrums tajā konkrētajā vidē?
Tieši tā. So, parasti...
Tas sanāk tā, kad tā ultraskaņa iet caur vairākiem orgāniem, tad tur kaut kā, jāsaskaita kopā?
Jā, tieši tā. Tad īstenībā mums vajag zināt šo ātrumu, bet šis ātrums principiāli nemainās, par cik pārsvaru visur ir ūdens. Tad cilvēka sastāvā pārsvaru ir ūdens, protams, ja tur būs tādi sablīvēti tauki, tad ātrums arī būs cits. Mums to vajag paredzēt, un tam cilvēki strādā savu zinātni. Notiek visādas kalibrēšanas, lai to panāktu, jā. Bet, pieņemsim, pārbaudīt asins pulsu, jā, tam īstenībā šīs ātrums sevišķi svarīgs nav. Jā, par cik mums ir tikai puls, jā, ir C, jeb nav C. Es atbildēju uz jautājumu. Pārbaudīt kardiogrāfiju, pieņemsim ehokardiogrāfiju. Arī mums ātrums sevišķi nav vajadzīgs. Mums ir vajadzīga tikai kā parādība. Ir sirds puls, jeb nav sirds puls. Es atbildēju uz jautājumu.
Jā, paldies.
Some more questions, please. So, this is the example of the idea. So the organ has a motion with the velocity c. We direct the ultrasound beam with the frequency nu that reflects from the organ to the detector with the frequency nu star. And so, because of this, we can measure the difference between nu and nu star and to identify this organ motion and its velocity. So the next one, lithotripsy. Sorry. So lithotripsy. So the idea of this technology is based on our knowledge that if we have the sound, means the sound propagation means the deformation of matter that sound propagates through. And because of this deformation, the deformation delivers the energy. And so we have the flow of energy. So in this case, this flow of energy may be directed for treatment. So anyway, we are saying that the sound wave delivers the energy. So we know this. Moreover, because the deformation, for deformation, we need to deliver the pressure. So this means if we have propagation of deformation, we have the propagation of the mechanical pressure. If we have the oscillating deformation, means sound, we have the oscillating pressure, and we say that the sound wave delivers the oscillating pressure. So now have a look what can be done. This is a patient and this is an organ, for instance, the stone in the kidney. And so we deliver the very powerful ultrasound pulse. This pulse delivers the energy, delivers the oscillating pressure, and in fact, this organ can be destroyed. So the stone is destroyed. So this is the lithotripsy technology. So in the previous century, in the 20th century, Riga Fest Hospital, the Riga Fest Hospital, delivered a little bit modern technology or advanced technology. So this is the ancient hospital that was established in 1803 for the very poor people. Today it is a modern hospital. You can see it hospital in the center of the city. And in the 1959 year, they applied for the first time so-called electrohydraulic lithotripsy. The inventors were Victor Holbergs and Dr. Leo Rose. So the idea of this technique is very similar to the ultrasound to generate the wave of the very powerful pressure, of a very strong pressure. So this is the electrode and this is the electrode too. Every way is water. This container is connected to the human body, to the patient body, and the discharge, electrical discharge, is delivered in this area. Because of the very powerful discharge, the sound is generated, and sound waves propagate through water to the patients. Actually, this boundary isn't so strong, and the profile of this cavity is like the acoustical lens, and the sound waves are focused to the kidney stone, and by this way the stone is destroyed. So there is a problem of navigation, how to know where is the stone located. So for this, typically we use the same sonography, for instance, or maybe X-ray technique for navigation. So please, the questions. Jautājumi vai viss ir skaidrs?
Ir skaidrs.
So now we're going to the new chapter, optics. So, and definitely the subject of our optics is the eye. Oops, what is this one? Okay. So this is our subject, the eye. If you go to understand the anatomy and the connection of the eye with other organs, we can find that we have two eyes, and each of them connects the area of the brains by the nerves. And have a look at this asymmetrical connection. So the left eye connects the right area, but the right connects the left one. So why, I don't know. So, but this is the nature, you see. So these hemispheres of the brain, the hemisphere of the brain processes this signal and delivers to us the feelings that we see. So the feeling is a very important, because from the further examples you'll see that really this is a feeling, because only the eye is able to see. The brain processes the information, the optical information, giving the feeling to eye. So this is the same scheme, more detailed, for instance, with demonstrations of the nerve wires. So you see some nerve wires nevertheless are going from the left one to the left hemisphere, but mainly they are going to the right, and so this one the same. So now let's go to optics to understand how the image is provided. What do you see here? Have a look attentively. You see the image may be changed in dependence on your willingness. Have a look next. You see like the slightly moved picture. Do you see it? Rotating circle. Please reply. Do you see it?
Yeah.
So, but they are stable. They are very stable. No any motions. Believe me. So you see the lines of the string actually, but it seems to you that they are not straight, but they are very straight. So have a look what is here. This is a very nice picture that assembled of different pictures, some pictures. So this is the face, this is the face, this is the arm, you see. So there is a combination, but in generally we see like the skull. So it seems to you that there are spirals. No, they are not spirals. Have a look. It's a circle, you see. So that is why the reality is something different that we accept, that we feel. So the brain processes information actually as they want. And we have like the illusion. Have a look here again. These lines looks like the bent lines, but they are very straight. So this is just a jokey picture. So this is again the picture like the fish. However, this is the face. You see the eyes, the nose, the mouth. You can say to me that the diameters of these orange circles are different. This is less and this is more, but they are very equal. They're the same. I'll try to prove it's very easy to do. You see? It's the same. So now have a look at the next picture. You can find huge collections of this, huge collection of similar pictures. What is the shelf? It's here, or is it here? And this is a beautiful one. What do you see here? What do you see here? The bird, or the very young, or very nice young girl? This is the face, the hand, the leg, and this is the leg, not the tail. So that is why, from the eye to the brain processes information and gives the illusion to us. Is this clear?
Yep.
And that is why very often we see that we want to see. Be very careful with this, because someone or somebody can see something different that the other one sees, because we see this that we want to see. So we don't speak about the brains. This is a very complicated area. People don't know exactly what is happening here. And we go to speak about the eyes. For us, the eye is the sensor of light. So design of the eye seems rather simple. So this is the eye, the sphere of the eye that connects to the muscles. And you can say, yeah, we know we need these muscles to change the position of the angle of this eye, to rotate it in this direction, or maybe in this direction or some other direction, to follow the motion of the object that is located somewhere here. You are right, but nevertheless, these muscles have one more aim, and we'll speak about this too. So this is a cross section of the eye. So we see that there is some lens. So this is a lens that consists of two lenses. This is a stable one, and this is the lens that is connected by the muscles to the wall, for instance, we say more simply. So what is the reason of these muscles? This lens doesn't have the muscles, but this one has. What is the reason of this? So next, definitely the light beam propagates here and meets the nerves, the wires, the yellow wire, I'm sorry, the wires that are connected to the brains. That's clear. But what is happening here? How the light transforms into the signal that is delivered to the brain. If we go here to this layer that actually transforms the optical signal to the bioelectrical signal that is delivered to the nerves, we can see different cells. There are two types of cells, so-called the rod cells, and like the cone cells. You see, their shape is like the cone. What is the reason that we have two types of these cells? So definitely you can say me, okay, if the cells are connected to the nerves, so the nerves are here, so this means that perhaps the cells deliver the signal to the nerves. That is true. But what is the reason that we have different cells? We'll speak about this too. So this is more simplified picture of the eye. Again, very clearly you see the lens, the stable one, and this is one more lens that is connected with the muscles. We speak about this one first and have a look what we have. This is the x direction, distance, and this is the lens. The lens has the ability to focus the beams. This is the place of focus. This is the object. The light beam goes, we select just two beams. One goes to the lens in the perpendicular direction and is directed to the focus. All of the parallel beams are collected at the focus. And now we get the second one beam, this one that goes through the center of the lens, and because of this beam doesn't have any refractions. So because of these two lines, we can identify the location of the image. Have a look. The image is here. So for instance, this is the person, the head is here, but we see our lens delivers the image of the head that is down. So actually, here we need to locate the cells, or actually the sensors, that are able to accept this cross point to deliver the signal that the beam is here, means the head is here, the other beam, the other cross sections for this object is located somewhere here, 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 and here, and because of this, we have an ability to assemble the entire image of the object. So this is the scheme that demonstrates what we see. This is the head, the real the object, and here we have the image. Actually, we can say that we see, I'll change this picture a little bit, I'll try, no, doesn't work. No, doesn't. Maybe the other side. No. Oh, this is good. Okay, very good. No. You feel my idea what I want to do. Oops. Doesn't allow. Okay, good. That is good. So actually, we see the object with the head below, with the head down. Inversion object we have. So the image inverts the object. So this means that we see that the top is here, the bottom is here, but it isn't true in life. But how do you know that really the top is here, means here, in spite that we see the inversion image? Can somebody explain?
Nu, jūs smadzenes pārtaisa otrādi.
How do the brain know? Tad kā mēs zinām, ka cilvēks tiešām stāv normāli, nevis ar kājām gaisā? Kā mēs to zinām? So actually this is a question of the gravitation vector direction. How do you know that the gravitation vector is delivered in this direction? Actually, we see that the gravitation is in this direction, but how do you know this? The answer is very simple. From the first hour of our life, we feel gravitation. Next, our first falling down, our personal experience, we know that we are falling down, following the gravitation vector. And our brains became accommodated for this event, and they deliver the information to us that really the gravitation is directed this way, and the head is here, in spite that optical image is directed vice versa. So again, have a look. The brains, they do whatever they want, just to make us happy. Vai tas ir skaidrs? Alô, atbildēt. The questions, please. I don't hear you. Please reply.
Jā,
Wait,
es
that much?
skaidrs.
Okay. So everything to process the image is happen here. So it's a feeling that the brains are much more clever than we, because they are doing for us something. So this is our picture that we started. And now what can be happen if the object is moved in this direction? Let's go to consider. Have a look. These two beams, this one and this one, now have the crossing point somewhere here. This means that the image is here. But the cells or the sensors are still located here. This means that we don't see this image. We can't detect this image. What is necessary to do? Please, your recommendations. What to do?
Nobīdīt fokusu.
Yeah, this is just one way to change this focus. How to change this focus? Again, only one way, to replace this lens. But can you imagine, for instance, the teacher is in front of you, and now it is closer, and you very fast going to change the lens. to take off one eye and to get in the second one. So it is impossible. So that is why we have to have the lens that is adjustable to the motions, actually to changes of the distance in between the object and the lens. Now have a look. How does this mechanism work? So again, if you change this focus, everything is fine. The image is here. So this is the design of the lens. I can say that the lens may be assembled of the small prisms. Now let us go to consider the prism. So this is a single prism. This is a perpendicular to the surface of the prism. And this is a beam. Because of the refraction coefficient, the beam changes the direction. It's well known. So this refraction coefficient is a sinus alpha to sinus beta. So these angles may be changed, measured, etc. For the human lens, this coefficient is 1.42, refraction coefficient. And this means that the angle alpha is larger than the angle beta. So if you say that we need to change the lens, so let's go to do this. So this is a prism. This means that we need to change the angle of the beam, of the refraction of the beam. For instance, from this one to this one. Let's build the other prism, you see. Compared to this prism, has a different angles, and that is why the propagation is different. Now we go to assemble of these prisms, the lens of these prisms. So the prisms are here. If I provide the tension forces in this direction, so this prism changes the shape and becomes like this one. Is this clear? Это ir skaidrs? Hello.
Jā, ir skaidrs.
So this means that here I need to have the forces. I need some muscles here. The second point, this material must be rather elastic to provide the muscles the ability for these tensions, for these deformations. So from this lens to this lens, I have different propagation angle for the beam, and the beam may be focused at different position and different focus. So have a look. These are the muscles that deliver the deformation of the lens. With age, this polymeric material, the lens material, becomes not so elastic, becomes stronger. It's coated with some polymeric films that don't give or decrease the elasticity of this material. What to do? The first one, to change, to replace. But this is a surgery operation. So that is why any surgery is intervention, I'm sorry. So that is why people are doing something different. They locate here in the front of the eye the compensation lens that compensates this inability of deformation, actually to change the focus a little bit. So there is one more option to postpone this time when the lens are necessary. This time will become to each of us. I already use the glasses. So somewhere in 50, maybe 40, maybe 60 years, you'll become to the glasses too. So this is life. This is a biology. We can't be against this life, against this biology. But we can postpone this time to the later years, to the more older years. So because of training, we can train these muscles to make them more trained as any muscles and they'll have the ability to deliver larger forces for deformation of this lens. And that is why we postponed the time, the age when we need the glasses. I knew one guy, unfortunately he passed already away, but he didn't use the glasses until the finish of his life. He passed somewhere 90 years old. And he trained these muscles by the specific exercises. So next time we go to speak about the optical compensations to use the lens. So what are the questions for today? Kādi jautājumi šodien? Alô? Lūdzu jautājumi. Nav jautājumu, lūdzu atbildēt.
Nav jautājumu.
Nav, okay. Tad in 3 minutes you have the open test. So good luck. I'll stay online somewhere in 10 minutes. If you need to ask me, please ask.